Hello and welcome to a new video in a course on linear algebra. In the previous videos, we introduced the basic definition of vector spaces and we discussed some basic examples of these. In this video, I plan to cover some properties of vector spaces. And from now on, since we're getting towards the end of this chapter and we'll be getting into linear transformations and matrices, I advise you from now on to grab some coffee and get yourself prepared for some more denser material. So let us discuss some properties of vector spaces. So I remind you a vector space is this set where we equip it with addition and scalar multiplication, and we require some axioms to be satisfied. So we're going to use now the axioms that we have. We're going to use the axioms defining the vector spaces to prove some properties of vector spaces. Alright, so here's the first property of vector spaces, and it is that the vector space cannot have more than one zero vector. So the zero vector is actually unique. And as we go in these properties, I advise you to grab a piece of paper and write these proofs. And write these tricks appearing in the proofs, because these are tricks that you're going to be using over and over again. So here's the first trick, or here's the first trick appearing in the first proof. So to prove uniqueness, usually here's what you do. You say, suppose there are two. So, for example, in this case, we're proving the uniqueness of zeros. We're gonna say, suppose there are two zeros, right? And let's call these 0 and 0 prime. And what we're gonna do is that there are two ways here. Either we're gonna prove that 0 is equal to 0 prime, or we can prove that if we start with the assumption that 0 is not equal to 0 prime, we reach a contradiction. So we're gonna over here there's a proof, there's a direct proof, and here this is a proof by contradiction. So I'm gonna present the two proofs real quick. So we suppose that 0 is not equal to 0 prime, but then if you start with 0 prime, you use the axiom that 0 itself, it's a 0 of the vector space, thus adding 0 to any other vector gives you the vector back. Thus, if you add 0 to 0 prime, if you add 0, the vector 0 to the vector 0 prime, it should give you the same thing. This equality is then justified, right? So, but then you use the fact that 0 prime is a 0. But if 0 prime is a 0, then adding 0 prime to any other vector should give you the vector back. And specifically, adding 0 prime to the vector 0 should give you 0 back, right? And thus you just proved that 0 prime is equal to 0, and this contradicts your assumption. Thus it must be true that 0 prime is equal to 0, and in other words, the 0 vector is unique. All right. And as you see, you can also do it directly. Like you can just say, well, 0 prime is equal to 0 prime plus 0, since this is a 0 vector, and then this addition is equal to 0 because 0 prime is itself a 0 vector, and thus you prove that 0 prime is itself 0. So this is the first property, and it is called the uniqueness of the additive identity. Alright, so the next property that we're gonna cover is what's so-called uniqueness of inverses. So as you will see later, these properties are important in proving harder theorems. So you must know these, and you must know the tricks behind the proofs, right? So we mentioned that one of the properties of vector spaces is that if you start with any vector v, any vector, you can find another vector omega where when you add these you get a 0. In other words, you can always find an additive inverse, right? We defined what additive inverse is. So this proposition is saying that this additive inverse is unique. And what does that mean? It means that you cannot have more than one inverse to the same vector, right? So again, how would you prove uniqueness? Well, one way to do that is to suppose that there are two, and then to prove these are equal, these are the same, or you suppose that there are two and they're different, and then you derive a contradiction. So let us do a proof, a direct proof here, and then we're gonna look at a more cleaner solution. Let us do it up here. So to do a proof, you usually should do it in the very general case. So you start with a vector v in the vector space, right? So let v be, this notation is for in, right? Or belongs. So let v be in v. Let v be in the vector space v. We know that there is an inverse to v. So let us say that suppose there are two inverses to v, and let's call these omega 1 and omega 2, for example. Since v is since omega 1 is an inverse, then v plus omega 1 is equals to omega 1 plus v is equal to 0, and at the same time omega 2 is an inverse, and thus v plus omega 2 is equals to omega 2 plus v is equal to 0. So these are the defining characteristic of what an inverse is, right? So what we're gonna do is that we're gonna prove that omega 1 is equal to omega 2. And how are we gonna do that? Well, we're gonna start with omega 1, right? And here's what we're gonna do. We're gonna say that omega 1 is equal to omega 1 plus 0, right? Why? Because you know, by the definition of 0, if you add it to any other vector, you get 0 back. And now we're gonna replace this 0. You see the 0 here? We're gonna replace it by some of these. Like, we're gonna replace it by this thing here, right? Or let's say this thing here. So it's gonna be omega 1 plus v plus omega 2. You see? We just replaced the 0 by its value. And then we're going to use the property that omega 1 plus v from here is actually 0. And this is 0 plus omega 2. And thus omega 1 is equal to 0 plus omega 2. And this is equal to omega 2, since adding 0 like keeps the vector the same. And thus we just proved that omega 1 is equal to omega 2. And this proves uniqueness, because if there are more than one inverse, it must be the same. So thus it's unique. And here's a cleaner proof. I replaced here like my omega 1 here is omega, and omega 2 is minus v, right? So these are cleaner proof. So you can look at this. All right, so please keep track of the tricks that we're using, right? We suppose there are two, and we prove they're the same. This is a proof of uniqueness. All right, so since we'll be seeing a lot of proofs of existence and uniqueness, it is important to see some basic proofs. And here's one additional property of vector spaces. Like, if you start with a vector space V, and you take any vectors omega and V, then this equation over here has a unique solution. And this requires two proofs. It requires a proof of uniqueness and a proof of existence in the first place. So the has part requires a proof of existence, and the unique part requires a proof of uniqueness. So what does existence mean? Well, it means that you should prove that there is at least one x that satisfies this equation. And what does uniqueness mean? It means that there is exactly one x. And how would you prove that there is one x? Well, you find one x. And how would you find such a one x? Let's see. So x should take the form, if you look at this, x should take the form omega plus something that cancels the v, right? I hope you agree with me, because we want to get omega back, right? And we want to cancel the v in some way. And what is one way of canceling an element in a vector space? Well, it's by adding to it its inverse, right? So what we're gonna do is that we're gonna do a proof in a very general way. So we're gonna first prove existence of 1x, at least 1x, right? And to prove this, we're gonna start with two general vectors, v and omega, in the vector space v. So it's gonna be in the vector space v. And we're gonna take x to be omega plus the inverse of v. Why are we gonna do that? Because remember, this is the motivation for that. So we're gonna take the inverse of v. So let's call this minus v, right? Because remember, we denoted the vector minus v to be the inverse of the vector v. So if we now add x plus omega, what do we have? Well, we have omega plus negative v plus omega plus v, excuse me. And now v plus negative v plus its inverse is 0, right? Remember, we haven't defined subtraction now, but we're denoting the inverse as negative v, and this is how we're going to define subtraction of vectors. So this is going to be omega plus 0, and omega plus 0 is again equals to omega, because 0 is the identity. And I'm gonna tell you here something that is important when you're doing proofs. So usually when doing proofs, you have to justify every step. So for example here, so here we jumped, we made an assertion that the addition of these is 0, and we have to say because this is by the additive inverse property. Right, we have to justify our equalities, and here we made a new move, and we have to justify it, and the justification is that this is an additive identity. So 0 is an additive identity like by the additive identity property you have this. So this proves existence, right? And the next thing we're going to prove is uniqueness. And what does uniqueness mean? It means if you start with more than one x satisfying this equation, it must be the same x. And one way to do that is to look at this equation and say, well, this equation has a solution, which is what? Which is x, right? If x is a solution, right? If x is a solution to this equation, then we can add the inverse both sides. We can add the inverse of v both sides. So what we're gonna do is that we're gonna add the inverse of v, which we denote by negative v. This is gonna be omega plus negative v, and these two are just 0, because remember we should justify this is by additive identity. Additive inverse, excuse me, and thus we have x plus 0, and thus we have x. This is because x plus 0 is equal to x by the additive identity, and this is going to be omega plus negative v. So we started by saying if x is a solution, then x must be this, and thus x must be unique because there is one possibility for x, right? Alright, so I hope that you're keeping track of the tricks appearing in the proofs. Alright, let's do the next property. This property is saying that if you start with any vector space and you take any vector in that vector space and you scale multiply that vector by 0, then you should get the 0 vector. So I remind you, this is a number, right? And this is a vector, and this is scalar multiplication, right? And this is the 0 vector. So this is a vector. And we want to prove this. I'm going to give you two different proofs of this. So the first one is going to use the proposition that we just proved before. It's the uniqueness of the solution to this equation. and the other is going to use a different thing. So let us see what this proof is. I'm going to just go over this proof because the other proof is more important. The idea is that if you look at 0 plus v, this is equal to v, right? And this is by the additive identity property, right? This is the additive identity property. And thus, if you look at 0, 0 is a solution to this equation, right? 0 is a solution to this equation. And if we can prove that 0 dot v is also a solution to this equation, then we can then we get, by uniqueness, we get that 0 must be equal to 0 plus v. So let us see how we can do that. Well, 0 dot v plus v is in fact equal to 0 plus 1 dot v, and this is by distributivity. Remember, in vector spaces, expansion, quote-unquote expansion, is allowed, and this is due to distributivity property. So you can take the 0 from here and the 1 from here. And why is this the case? Because remember, there's a property called the multiplicative identity, which is that if you multiply v by 1, you get v back, right? So this is 0 plus 1, and what is that? These are numbers, right? These are the real numbers that you know. 0 plus 1 is just 1, and you use back the multiplicative identity property, and you get v back. So we just proved that 0v plus v is equals to v, and 0 plus v is equals to v. This we know by the multiplicative by the additive identity property, and thus by the previous proposition, by uniqueness of the solution to x plus v equals to v, we have 0 is equal to 0v. So again, I'm saying here, we have two solutions to the same equation, which is xv equals to v, and we proved that in vector spaces this equation has unique solution, and thus these two solutions must be one and the same, and thus 0 is equal to 0 dot v. This proof is interesting, but I would like to give a different proof, because it's a more known proof, and it's a more interesting proof that has an interesting trick. So here's the proof. So the proof is that so here's what we're gonna do. So I'm gonna tell you what the trick is. So we're gonna start with 0 dot v. Now this 0 dot v is itself equal to 0 plus 0 dot v. And why is that? Well, because 0 plus 0, these are numbers, is equal to 0, right? So 0 dot v is equal to 0 plus 0 dot v. And then we're gonna use distributivity. So again, you should justify all the steps that you're doing. So this is gonna be 0 dot v plus 0 dot v. And now what we're gonna do is that we have the equation 0 dot v is equal to 0 dot v plus 0 dot v. What we're gonna do is we're gonna add the inverse of 0 dot v both sides. So since 0 dot v is a vector in the vector space by closure of scalar multiplication, then it must have an inverse. So let us mention that by closure 0 dot v is in v. It's a vector in v, and thus has an inverse, which we can denote by 0 minus 0 dot v. So let us denote it as such. And now let us add it both sides to this equation, adding it. What do we get? We get 0 dot v plus negative 0 dot v is equal to 0 dot v plus 0 dot v plus negative 0 dot v. And now I'm running out of space, but to like long story short, these things will cancel and give us a 0 because these are inverses, and it's going to be equal to 0 dot v, and these things will cancel and give us a 0. And now by the additive identity property, 0 dot v plus 0 is 0 dot v, and thus we just proved that 0 is equal to 0.v, which is what we wanted, right? So this last step is by additive identity. So please again keep track of the tricks appearing in the proofs. Okay, so on to the next property. So the next property is that -1 times v is equal to -v. So yeah, it might seem a little bit ambiguous here, so let me justify. So by -1, this is a number, right? And by v, this is a vector, that this is any vector in the vector space. By -v, we mean the inverse of v, right? So remember, we denoted the inverse of v by -v. So what are we saying here? We are saying that so -1. So we're gonna define in a few that the subtraction of two vectors is allowed by saying that by this property, right? So the reason subtraction of two vectors is allowed is this property, and we're gonna see why. And then we're gonna define subtraction of vectors. So here's a new trick when proving things about vector spaces. If you want to prove that something is an inverse, or something is an identity, or any other, if you want to prove something satisfies a property, you have to check the property for that thing, right? So let me just make myself clear here. So we're claiming here that -1 times v, so the scalar multiplication of -1 times a vector v is equal to the inverse of the vector. But to prove something is an inverse, we have to check the property of the inverse, right? So to prove that this is equal to the inverse, we have to check that the property of the inverse holds for this, right? So let us see how we can check this. Well, to check this, we're gonna check that v plus -1 times v is equal to 0. So this is what we need to check, because if we check this, we'll be proving that the -1 times v is equal to v. And why is that? Well, because we proved that the inverse is unique. So if we have two inverses of the same vector, it must be the same thing, and thus the -1 times v should agree with the inverse of the vector. So let me just prove this real quick. Well, so again, to prove this, we need to start with a general v. So let v be in v, and we want to prove that this equation holds. So let us see why. Well, v plus -1 times v is equals to 1 times v plus -1 times v. And why is this? This is by the multiplicative identity that says multiplicative identity property that says that 1 dot v is equal to v. And we now use distributivity property, which is that dot v. So here we use distributivity, right? And what is 1 plus -1? This is 0, and thus this whole thing is 0 dot v. And we just proved in the previous proposition that 0 dot v is itself equal to 0, right? So this is by the previous property, and you should justify every step. So this is by proposition 3.4. So this is getting a bit messy. So let us see the cleaner proof. So the cleaner proof is that we're gonna start with a v in v, and we will use the property that this is a multiplicative identity. One is a multiplicative identity, and then we're gonna use distributivity. So here we have distributivity, and here multiplicative identity, and thus here we have this is 0, and this is by the previous proposition that we just proved, we get that this is 0. Before wrapping up this video, let me just define subtraction of two vectors for you. Let v let V be a vector space, right? Then V and omega, let's say that these are in V. We define V minus omega, the subtraction of two vectors, to be V plus minus omega, right? And this is just V plus negative 1 dot omega. And I'm gonna keep the examples and non-examples of vector spaces to the next video to discuss.